All right, well, we're back and we're going to take a look at the exhaustion method. Finding the area under a curve, exhausting all the little bits and pieces underneath or over. And we're going to do it by summations. And we're going to use a lot of rectangles. So these are the four formulas from the last video. You should have those down. We're going to reference those in this video. And we're going to find the area bounded by the same function from the last, x squared minus 1, the y-axis on the interval x equals 1 to x equals 2. Now last time we looked at using it and creating a summation formula with 4 rectangles. 4. Okay. How many rectangles do we want to use now? Well, I like to change the game. And what I'd like to do is this. I would like to use a total of n rectangles. That's right, n. Any number that you want. In fact, the bigger the better. The more rectangles we use, the closer we're going to be to the actual area under the curve. And we're getting there. The goal of this is to find that area under the curve to be exact, and it does tie everything we're doing into the integral. So if you're going, where'd the integral go? Well, it's still here, and it's going to relate to this sigma as well. So let's go through this, and let's do it this way to start if we could. Let's go ahead and create n rectangles. And let's say that we're going to do it as an upper sum to start. All right, you're going to need a little paper, a little space for this. All right, if we use n rectangles, the first thing we're going to have to do is we're going to have to figure out the width of each rectangle. Well, to do that, we're going to subtract our boundaries. 2 minus 1, and divide by the number of rectangles. So the width of each rectangle is 1 over n. If I'm using 10 rectangles, each width is 1/10. 100 rectangles, 1 over 100. Now the next thing I need to do is I need to write my formula and as a summation, but I think what I'm going to do first is I'm going to break this up. And I'm going to write a formula for the height of each rectangle if it's truly going to be an upper sum. Now that's going to involve the function. Now if I want an upper sum, because these values, remember the values kind of look like that. Okay, it was increasing and it was monotonic. So increasing always on the interval. We wanted the numbers coming on the right side, didn't we? So we wanted the 4 biggest ones. So let's think about how we could write that. Well, we would write that with the 1 plus, and we would use the width times I. Think back to when we used 4 rectangles and how that played out for us then. Now we're going to combine those 2 pieces and write a summation formula. So, and we're going to do it like this. So let me back up for a second, because we don't know how many rectangles that we want to use. So you know what? We can use as many as we want. So let's call it, we want the number of rectangles to approach something really large. So let's put this on here. The limit as n approaches infinity of the sum from I equals 1 to n. Now this is the width and the height of a rectangle. So the width is 1 over n. And the height is going to be this right here, but I'm going to write this just a touch differently. I'm going to write it as 1 plus I over n, because I times 1 is just I. All right, so this is our formula. Now, believe it or not, I have to get a number out of this. And I'm not just going to put 1 in and then 2 in and 3 in and 4 until I get to like a billion. I'm not. I'm going to simplify this algebraically using these summation formulas that have a sum that's been proven already. Thank goodness for the work of people before us. And thank goodness for the work that you will do in whatever field of study, because that will be a benefit, I'm sure, to somebody else down the road too. So this is going to be a limit problem, and we know that. We're going to come back to that. So let's just focus on the summation for a little bit. Because what I'd like to do next is I'd like to rewrite this part in here. And I'd like to rewrite it so I've got common denominators. So if you don't mind, I'm going to go ahead and write this as n over n plus I over n. And then I'm going to go ahead and keep my summation. Now you need to keep the summation. And let's go ahead and write that as over one denominator, and let's put it as n plus I over n. All right, now let's go up. Okay, as we move on up, we have to continue to simplify this. And so what we need to do is we need to go ahead and take this f right here, this f of n plus I over n, and we need to put n plus I over n into our function. Now don't forget, our function that we're dealing with is f of x equals x squared minus 1. So we're going to keep the summation, still necessary. Keep the 1 over n. And I'm going to put a set of parentheses here. And we're going to have to put this into x squared minus 1. So that's going to read as follows. X squared minus, let me back up, wrong thing. N plus I over n squared minus 1. And 1 over n is multiplied by all of that right there. Now, some things that you can do to make life a little easier for us. This 1 over n is actually a constant, and why is that? Well, we don't know what n is, but n is indeed a number. So what I'm allowed to do, just like when I derive and when I integrate, which we haven't talked as much about as of yet, I'm allowed to pull that out front. And so that's going to leave me 1 over n times I equals 1 to n. And now I'm going to square this out. This is n plus I quantity squared. So this is going to be n squared plus 2 ni plus I squared. Again, I have to FOIL that out, don't I? I can't square n and square I and be done. Bad algebra. Now, I also have to square the denominator. So this part represents the quantity that's squared. Now, I still have a minus 1, so because I'm going to need to get common denominators eventually, I'm going to make the 1 into n squared over n squared. All right, now some things that I can do. So one is, again, the summation has to stay. It's still a sum. Now I can combine some things, and I have an n squared and an n squared, and those go away and just become 0. So I'm left with 2ni plus I squared over n squared. Now, because I have an n squared on the bottom, and that's a constant, I can have it join the 1 over n out front, and that's going to leave me with 1 over n cubed times the sum of, from I equals 1 to n, of 2ni plus I squared. Well, we have to find an answer to this part. So what am I looking for? Well, what I need to do is I need to now use those summation formulas. There's one for I and there's one for I squared. Now 2n is a constant, but because it's tied into the I, here's what we can do. I can rewrite this as 1 over n cubed times the following. I can split this sum up because it's addition, just like this. So I'm going to make this 2n times I equals 1 to n of I plus I equals 1 to n of I squared. So I'm allowed to do that right there. So now if you look at the formulas, formula 2 and formula 3 from before, we can now make a substitution. So we're going to have 1 over n cubed, but now for the first time, I can remove the summation. Now the 2n stays, it's a constant. We don't need formula number 1 because that only applies if we have a constant completely by itself, and we don't. 2n, this constant, is a coefficient of I, not a constant by itself. So the I formula is going to be multiplied here. So it's n plus 1 all over 2, plus the I squared formula, not a very good addition sign, make it better, n plus 1, 2n plus 1, all over 6. And we're going to go up again. Okay. Well, as we move on up here, we need to simplify what we have. So let's go ahead and do that. So what I can do is I'm going to keep this 1 over n cubed right here. Now, this 2 and this 2 will divide out and become 1. Now, I have an n times n, which is n squared. And n squared times n plus 1 is going to give us n cubed plus n squared. All right, now I need to multiply all of this out. Okay, now each of those is over 1. I'll leave it like that. That's important. We'll get to that in a moment. So plus, now all of this is going to be over 6. Okay, so here's what's going to happen here. I probably want to do the binomial, take this binomial times that binomial first, and then take that times n. So just let me do a little scratch work off the side here. So multiplying 2n squared, 3n plus 1, and I'm going to have to take that times n. So that'll give me 2n cubed plus 3n squared plus n, because again, this is the product of the two binomials, and then I have to multiply that by n. All right, we're getting there. Now, you've got a lot of options to simplify on these as well. So if we focus on that simplifying part next, slide on over one more time here. At some point, we're going to need common denominators. So let's keep this 1 over n cubed, and let's turn these into 6s. So 6n cubed over 6, a denominator of 6, that would be the same denominators here. This would be 6n squared over 6, and if you don't mind, I think I'm going to go ahead and spread that 6 out between all the other fractions there. Now, let's combine some like terms. Still keeping the 1 over n cubed. And you know what I think we're going to do too? Since we all have a common denominator of 6, let's go ahead and bring that 6 out in front and make it 1/6. So now we can just focus on the numerator. So this will give us 6n cubed plus 2n cubed. That's 8n cubed. 6n squared plus 3n squared is 9n squared, and I have a lonely n on the end. Okay, so next step. Well, this term has been hanging out in front, the 6 combined with it, the 1/6 that is, and so let's go ahead and run it through everything. This will give us then 8n cubed over 6n cubed plus 9n squared over 6n cubed plus n over 6n cubed. Now, can we simplify? Yes, we can. Yes, we can. This is going to simplify to 4/3. This will simplify. Now, the number part might not be as important on some of this, but we'll go ahead and do it. That's 3 over 2n. And this is 1 over 6n squared. There's a reason why I said the number part maybe isn't as important. Because you know what? It's a limit problem. The limit as n approaches infinity. Well, if I put in a really big number for n in each of these terms, what happens? Well, this doesn't change. Well, 3 divided by 2 times something huge, that's going to be 3 divided by infinity. That's heading to 0. And if that's heading to 0, this surely will also be heading to 0 as well. So what do we find? Well, we find the result of the upper sum is 4/3. That represents the area under the curve if we use however many rectangles we want. 1,000,000, billion, trillion. That's what we're converging on. That's the sum. Wow. Pretty amazing. If we back up a little ways and take a look at all the work that we've done. Can't quite see it all, but there it is. 14 feet of whiteboard space about, and we're half done. We're half done. So, and you're going, what do you mean we're only half done? You're looking at the time in the video going, we're going to do the other half in the next video. Well, fortunately enough, there's a little theorem that says if we do the upper sum and the lower sum, we're going to get the same result. So if we do the lower sum, we're also going to get an area of 4/3. Now this leads us into some really nice things dealing with integration. But I also want you to think of the magnitude of what we've just done in this video and what you followed along with as well. So if you were to go ahead through this and count how many things we had to do to get a final answer here, it's a significant number. Maybe the most pieces of algebra that you maybe had to put together ever. So what does math teach us? Well, I think what you can learn from this and what students have learned in the past is the discipline that you have to have. With the jobs that you might want to have someday, how disciplined do you need to be? Okay? To go through an entire situation like this, mistake-free, it's very impressive. And there are some occupations, a lot of occupations that count on you to do that. Being a surgeon, a pharmacist, all kinds, lawyers, to say the right things at the right times. So this is one of the reasons why we do math. It teaches you discipline. Okay? It teaches you order. And are you capable of doing that? Yes, you are. It takes practice. It takes work. And as you go through this and navigate this, some of the most important things are getting it started right, getting it set up, giving yourself a chance, giving you yourself mentally, that chance as well. Hey, we'll be back in future videos to talk. I'll talk with you more. Right now I'm hearing bells, so and you are too. Have a great rest of your day, and we'll see you again soon.